Today we'll move from graphing radical expressions to simplifying radical expressions. And in order to do that, we need to follow these three rules. First of all, no radicand can have perfect square factors other than 1. So for example, if I were to look at square root of 3, that would be a simplified radical expression because there are no perfect square factors of 3 other than 3 in itself, and 3 and 1. However, if I look at the square root of 8, that's not simplified because there's a perfect square factor within that of 4. 8 is 4 times 2. Likewise, no radicands can contain fractions. In other words, there are no fractions underneath the radical sign. So if I have something like 3/7 under a radical sign, that's not simplified. If I have something like the square root of 3 over 5, that's okay because the radicand itself doesn't have a fraction within it. And then no radicals appear in the denominator. Well, that means something like 2 over root 5 can never exist. A couple other properties that are going to help us in this simplification process are the following. If I have the square root of a times b, those factors can be separated into two independent square roots multiplied together. Likewise, if I have a fraction of the square root of a over b, that can be split into the square root of a over the square root of b. And we'll see how that helps us in a couple of examples to follow. First, we start with the square root of 24, trying to simplify that. I know there's a perfect square factor in 24, and what I always want to do is find the biggest perfect square factor that goes in. So in this case, my largest perfect square factor is 4 times 6, which is 24. I can break that apart into the square root of 4 times the square root of 6, and the square root of 4 is 2 times the square root of 6. Square root of 6 is simplified, so we say this answer is 2 root 6. I move over to the square root of 135, and I don't think 4 is going to go into 135. That's the first perfect square I check. I look at 9 and I find out that 9 actually goes into 135 15 times. And I can split that apart in the square root of 9 times the square root of 15. Square root of 9 is 3 times the square root of 15. There are no perfect square factors in 15, therefore this is simplified. We move on to variables under the radical sign, and remember, a perfect square is something multiplied by itself to get you that number. So if I look at x cubed and y to the fourth, I notice right off y to the fourth is y squared times y squared. That's a perfect square. X cubed, there's nothing multiplied by itself to get me x cubed. But what I can do is I can say, well, x cubed equals x squared, which I know is a perfect square, times x, and that's all multiplied by y to the fourth. So if I want, I can separate any product of factors into separate radicals. That's the square root of x squared, square root of y to the fourth, and the square root of x. Square root of x squared is x, square root of y to the fourth is y squared, and there is no square root of x. So this is the simplified form. When I take a look at this next term, it combines a number and variables. In 75, I know that's 3 times 25. 25 is a perfect square. Y to the 12th is a perfect square because I know, or x to the 12th, sorry, x to the 6 times x to the 6 is x to the 12th. Nothing multiplied by itself gets me y to the 11th, but I know that if I split y to the 11th up into y to the 10th and y to the 10th is a perfect square because y to the 5th times y to the 5th is y to the 10th. In general, any variable with an exponent will be a perfect square if it's even. So for instance, y to the 50th is y to the 25th times y to the 25th. Y to the 44th is y to the 22nd times y to the 22nd. So really, if you see an odd power, all you need to do is subtract 1 from that power and you'll have a perfect square. So anyways, let's get back to this problem. I can break this apart now into factors. Square root of 25, square root of x to the 12th, square root of y to the 10th. What remains is my 3 and my y. Square root of 25 is 5. Square root of x to the 12th is x to the 6th, and y to the 10th is y to the 5th, root 3y. And that satisfies all my conditions of being a simplified radical. We'll move on to some fractions. What I like doing first is seeing if within my fraction I can reduce anything. And in this case, I can. 2 over 50 reduces to 1 over 25. And just luckily, when I reduce this initial fraction, I end up with a perfect square. What multiplied by itself is 1/25. That's just 1/5. And now it satisfies all my conditions. No perfect square factors under the radical because there is not a radical. And because everything's removed from the radical, the problem is done. Now in this problem, nothing simplifies. 5 over 4 doesn't reduce. So what I can do from here is say, all right, well, I know I can split this fraction apart into 2 fractions. And you'll notice now that in my denominator I have a perfect square. So what that gives me is the square root of 5 over the square root of 4 is 2. I have a radical that has no perfect square factors in it in the numerator, which is okay. There's no radical in the denominator, so this satisfies all my conditions, and I'm done. And that's pretty much all we've got. Fill out your lesson summary and solve these problems below, and we'll chat more about this tomorrow.